Hi. I'm Jan. My name is Jan Lehnard. I'm a software developer from Berlin. Welcome to Berlin. I hope you're enjoying the city. Who here is not from Berlin? Right. I hope this is a great day for you. Also, thank you. I have a little bit of help with this whole event, so it means a lot for you to just buy a ticket and be here and enjoy the show. Thank you for coming. If you've got any questions, there is a little bit of time for Q&A afterwards, and I'll be around so we can chat while you're all here. But if you think of a question after we've all gone home, here's my email address. Feel free to email me. I like receiving email. And if you do the Twitter, you can follow me as well, if you want. I'm one of the core developers of Apache CouchDB. And I'll be talking to you about a CouchDB implementation. Meaning that we'll do a rather hardcore technical deep dive into what makes CouchDB work. And I hope to show you that CouchDB is incredibly clever in the way it does things, and I hope you agree at the end. But we'll see. Who here knows, who has heard of CouchDB? Probably everyone, right? Right, that wasn't all hands. Anyway, who's using CouchDB? Right, a few. That's cool. Who's looked into the internals? 1.5, 2.5. Yeah, cool. That's good. So it should be good for everyone here. Just to reiterate really quickly on why we should care that something like CouchDB exists. I'm showing you the new project motto. You'll be one of the first people to hear this. This is a brand new slogan that we've got. And it's crazy revealing, right? CouchDB is a database that replicates. It's deceptively simple, and we only want to convey a few things with this. So CouchDB is a database. If you're in IT and you hear something says DB, it's probably a database, so that's kind of given. But we do take data storage very seriously. If you trust your data to CouchDB, CouchDB does everything it can do to honor that trust and give you the data back whenever you ask for it. It also does clever things to the data that you can find it in very efficient ways and do clever things with it. And then there's a bunch of features in CouchDB that are really, really cool, or that have certain advantages over other things, or have interesting trade-offs. But the one feature that everybody agrees on who works on CouchDB or who uses CouchDB is its replication feature. So that's why we put it in the motto. CouchDB is a database that replicates. And replication can mean a lot of things to a lot of people. In CouchDB land, it means synchronization. It means I can replicate a database to a second database. And this could be on the same machine, a different machine. Could be on a phone, could be on the other end of the world. It can go back and forth. And that is CouchDB's true killer feature. And to help to elaborate that a little, or to make this a little bit more understandable or visible, is I prepared a quote for you that's also very exclusive. Think of CouchDB as Git for your data, for your application data. See, I screw up my own quote, sorry. So think of CouchDB as Git for your application data. And Git not in the way that you have a bunch of versions and you have a big merging algorithms and diffing and you can rewrite history and everything, but Git in the way that you can have data in a location where you want to do stuff with it. So say I develop some new software on my computer over here, so I'm writing the software, and I'm showing it over to Steve, and he clones the repo, and he can look at my code, and he's like, I found a bug, I fixed it, so he pushes, or I pull the fix from him, I keep working, and he shows it to Mary, and Mary then fixes 2 more bugs, and she pushes them to me, and eventually we're all happy with the work, and then I push it to GitHub, and our continuous integration server sees, oh, there's a new change on GitHub, so I maybe I go and check that out and run it through our integration test suite, and that all passes, so the CI server says, hey, this is good code, I push it to production or a staging environment and mark this good code. The magic here is that not that you can do all this crazy shit with Git, but that you can have the data locally where you want to do a specific task with it. And CouchDB gives you that, but for your application data. In a more specific example, say we have an office in Berlin, and you have a little bit of like internal office software that your employees use to manage customer data. And things are going, you store stuff in CouchDB, it's just a server in your office, all cool. And things are so successful because of this really great internal tool that you've written that you need to open a New York office over there. And maybe you put the the local server in Berlin on a public IP, so the New York people can access it, and then they complain, well, it's too slow, because it has a, whatever, 200 millisecond delay for every single request and user interaction, and it's really cumbersome to use, kind of like GitHub on our end, because it's in California. Maybe you upgrade to a bigger line, but then your internet provider craps out for an hour, and then the people in New York can't work anymore, and it's like after hours here, so we can't get technical support going, so all that sucks, and the people in New York can't do any work anymore either. So that's all bad. You can put it in the cloud somewhere, but then you have to trust all that data to the cloud, which is a questionable thing to do at this point. Eventually, though, you realize, oh, I have a CouchDB here. I can just have a full copy of my data in the New York office, and you set up another server, and the application runs there, and all the New York people can access the data locally. It's fast. It's on the local network, gigabit, and everything. And it can replicate the data to Berlin, so we can all work on the same data. And if there's an internet outage, well, we don't really realize because we all have access to the local data over here. And when the internet comes back up, we can replicate and go again. And this works really well as well, so that you have to open an office in Tokyo. We love Tokyo, right? And then you can set that up as well, and you can replicate things around. So that is one of the scenarios where that CouchDB replication is really useful. Another one, for example, you have a bunch of couches in a data center somewhere. Maybe that's a big cluster that holds a bunch of user data, and then your users are maybe you have a website, and you have per user data on that website, and maybe you have a mobile app, an iOS app, an Android app. And you want to use the same system, and that's entirely possible. There's two pieces of software that complement CouchDB in that whole scenario. The one is CouchDB, the other one is TouchDB. We are very creative with names, I know. Mean people call it the star ouch family of databases, but we don't like that. CouchDB is implementing that whole replication protocol, which I'll explain later, in JavaScript for the browser. And that may sound crazy, but if you ever used a web app in the subway in Berlin or on a plane with no Wi-Fi, you kind of know why it would be useful to have a local, fully available local replicating data store in your browser. So CouchDB is that, and allows you to build fully offline web apps that replicate to a big cluster in the back end. And TouchDB is the same thing again, yet again written, or it's a different implementation yet again, and written in Objective-C and Java respectively for iOS and Android, so you can have the same scenario in your mobile apps if you want. So this is quite cool. So this is the cool shit that CouchDB does, and there's other stuff. It's a document store, uses JSON for storage, HTTP for transport, interesting indexing solutions and everything. But this is the cool stuff. And that's just as an intro for people maybe haven't looked too deep into Couch. Now let's jump into the technical bit. If we look at any database, just pick any database, and then we'll cut through it and look at the layers in that database. Every database, any database, looks like this. And may actually look like this. There's the operating system somewhere down here. There's a file system, which is still part of the operating system. And we're finally getting to the database part over here, where there's file system access. And on top of that are the core data structures that power everything. And on top of that, we have the core features that do things with the core data structures to provide something to the user, or provide the value. And then on top of it is the API that makes everyone, gives users access to these features on top of the data structures and everything. So this is every database, literally. And you may know why I'm into databases. I love this cake. So this is my daily bread and butter. It's cake. I like it. Sorry. And CouchDB in particular is no different. We have a file system. On top of that sits a module called CouchFile, then a module called CouchDB Tree, then a bunch of modules, CouchDoc, CouchReplicate, CouchMetroReduce, and all the core features of CouchDB sit on top of that. And then yet, at the upper level is a big module called CouchHTBD, which is the user-facing API implementation. And we'll be looking at the middle three bit. I'll start in the middle, jump down, and then up again, because that makes the most sense in my narrative. So far, any questions? I don't think so. I don't know who made that cake. Let's look at the core data structures. CouchDB's core data structure is a B+ tree. And if you've done CS, computer science, you know probably B plus tree does that. So it's a special form of the B tree, which is not a binary tree, but a B tree. It's very it's a trick question in that kind of sense. B trees are very wide, shallow, sparse, and the plus variety means that it actually has all the usage data only in leaf nodes of the B tree. It's a generic picture of a tree. That is what we think of a tree, which is it's actually two trees that look like 1.5, but a B tree looks more like this. It's very thin in the beginning, and it spreads out really wide, and all the actual stuff is in the top leaves over there. I'll go into more details of that. So this B plus tree is the core data structure for most of the important things, or for the most important things in CouchDB. At first and simplest, this sorry, one more thing. The B tree obviously gives us an ordered access to data. So I can look something, or I can find something in the B tree, but also can ask for a range or the order of stuff. That's important here. The first thing that we implement with this B tree is an by ID index. Kind of looks like this, big table basically, and it has a bunch of slots. And when we're writing any data, for example, document G, it goes over there. If we write document D, it goes over there, and then we write document K, it goes over there. So far, so clear, but in reality, of course, we build the data structure as we start out, so it actually looks like this. We don't have empty slots. It's not a hash table. So it's like a mini tree over there, DGK, stored in order and clustered together. So this is very basic. If ever the smallest unit of data in CouchDB is called a document, which is a serialized JSON object, and every one of those has an ID, and this ID goes into this by IDs index. So whenever you have an ID of an object or a document, you can look it up in the by ID index. Very easy. There's a second index, though, that is in the core data storage called by sequence. And it is designed to answer the question, what happened since? And it looks like this. It has the same data, document DG and K, but in a different order. More specifically, in the order that they were inserted into the database. So the index is actually the 1, 2, 3. That's the index. And then the value for the value 1, or the index entry 1, is docg, then for 2, docd, and so on. What we can do with this is, what this does is record the history of the database since the beginning of the database. I know which document was written in order of its existence, or relative to the other one. So it's like a git log or SVN log for your database. And this is indexed, which means it's very efficient to look up data in there. So we can answer the question, what happened since the beginning of time for the database, and get a list of everything that happened. But we can also say, hey, what happened after 3? So, well, after 2, basically, in this case. So we would get back just the row with the number 3 over here. And this works over the entirety of the database, which is really nice. And I'll show in a few examples how this is the actual cool core data structure of CouchDB. Before I do that, though, we do another jump down to the file format. This is so interesting. The file format, also afternoon. Your minds are totally full with other cool technical stuff that has been going on here, but bear with me, the file format is actually very neat. So the setup here is that CouchDB is a database management system. There's multiple logical databases per system. So I have databases that have different names or managed by the same server, just like every other database as well. And then each database, the core storage of the database is represented by a single file in the file system. And then if we have secondary and tertiary indexes, these are stored in different files. But the core storage is a single file. And the 2 indexes I just showed, the by ID and the by sequence index, are both in the database file along with the data. They're interleaved. And I'll show how that looks in a second. It is also an append-only file structure for various reasons that I'll also show in a bit. So we'll only ever store stuff to the end. And CouchDB uses a multi-version concurrency control mechanism, or MVCC, to allow or it uses that and a queue of, what's it called? a serialized queue of writes for the database, so that writes can happen at the same time that reads can happen, and we can have any number of read requests to the database happen in parallel without writes ever having to wait or the other way around. So it's a fully highly concurrent data structure. And we have full control over fsync. Fsync is the magic thing that makes databases secure. It's a kernel, or what's it called? A system call. And by default, CouchDB opts to be very secure. But if you don't want to be as secure, maybe speed up a little, you can relax the fsync guarantees of CouchDB. Maybe for an index file that you want to write faster, but then it's OK if you lose it, maybe, so you can rebuild it quickly. So there's a bit of trade-off to be made. By default, though, all safe. And yeah, since it has both indexes, it can answer 2 questions, give me a document for a given ID, and answer what happened since. And everything else is built on top of that. Let's dive in. Let's have a look. Time progresses from left to right is indicated by this very fancy arrow. We create a new database. That creates a header. A header has a bunch of metadata information, the name of the database and some such, and pointers to the indexes. And currently, these are nil pointers because there's no indexes yet. So we created a database, and not much happens. That's pretty cool. There's also a checksum in there that makes sure that we have this is a valid data structure. And then we start writing a document. Document A, I will just append it to the file. That's just the raw value of the document gets stored there. And then we update the by ID index for the document A, and we store that at the end of the file. And then we update the by sequence index for document A, and we'll store it at the end of the file. And then we write a footer. A footer is the same thing as a header, but it goes at the end. Has the checksums and the pointers, and now these pointers actually point to the indexes, and which in turn point to the document over here. And then things get fsynced and committed to disk and are safe and never touched again. If we write some more, we can add document B. We'll write it to the end of the file behind the footer, update the index for B, the by ID index for B, update the by sequence index for B, and then write a footer that has the updated pointers to the updated trees. And those then, in turn, point to the previous versions of the versions down here, which then, in turn, point to the document A down there. So this is a data structure that always grows to the end of the file and never touches data that has been committed to disk. This is very important for safety. So this is the generic setup. And now you say, wow, updating 2 indexes for every single document update sure seems expensive. And you're sure right. CouchDB supports a thing called bulk operations. It does batching into bulks by default. So if a bunch of writes going into the same database, CouchDB will batch them for you and make a bulk commit for you. But you can also send it batches that you made yourself. And then it looks like that. We will write a batch of document A and B, and in one operation it gets flushed, appended to the disk. We update the indexes for A and B in one operation. That's more efficient than doing it once. And then again, the by sequence index in one operation, and finally append the footer. The situation is the same as before, basically, but all the intermediate steps are way more efficient. And of course, the batches are bigger, and depending on your hardware, your memory, your disk I/O, and all of that, you can have like batches of thousands or 10,000s, and these get committed way faster than every single one of them. And you create tighter data structures that are more memory efficient. And as good as CouchDB can, it will do that for you. I'll show you one more thing on top while we're here, how to delete a document. And things may not happen as you expect. So we want to delete document A. So we'll write the new value of the document A is now I'm deleted. And then we update the index A to no longer, the ID index for A to no longer contain A, and the by sequence index we write down that we deleted document A over there. And then we write another footer. So instead of removing a piece of data, we added 4 more pieces of data. How is that a delete? This is a mark as deletion, because, like I said, we don't ever touch anything that has been committed to disk. How we deal with actually removing stuff, I'll show you in a bit. So this is roughly how the call works. This has a few consequences. One, it's very efficient with storage. Consider a spinning disk. You all know this. Disks, there's 2 parts to a hard drive, a spinning disk, and an arm that finds the position on the disk to find spot where to write the data. It's really hard to make this and this really not good. And the more expensive operation in this case is finding the position on the disk. It's something like 4 to 15 milliseconds, I think, in modern systems. And then once we have found the spot, we can write hundreds of megabytes of data to the disk or read in either direction. It's really efficient. If we don't have to move the head. If we have to seek all over the place, then we'll be waiting tens of milliseconds per single request, and your CPU can do millions of cycles in the same time, so you're just wasting time over here. That's, if you have a big I/O weight, that's where it comes from. So CouchDB doesn't do that. It positions the head, or the write head, at a certain position, and then just keeps flushing the data to disk. So if you write a lot of stuff to CouchDB, you only ever have one seek and then write with near disk capacity, write capacity to the hardware. So this is really cool. And if you're sitting here like, wow, Jan, spinning disks, this is so 90s. We're all on SSD now, get with the program. That's also cool if you know how they work. At least the current generation, or the current storage class, do writes by allocating buffers in the storage layer. And if you can allocate bigger buffers in row, that's more efficient than having to allocate random buffers all over the place. So sequential writes are even faster on SSDs than random writes on SSDs. Of course, they're still way faster than on spinning disk, but the operational consequence for the data structure we chose and the way we use it is that it's both more efficient than not using this kind of thing on both SSDs and spinning disks. So that's kind of cool. It's cache-friendly in the sense that I explained the B tree is like very shallow, very sparse, and then it goes really wide. Each node in the B tree has about 1,600 entries for CouchDB. So even with millions of entries, we have a tree depth of like 4 or 5, I keep forgetting. And even for billions, it's just 6. And the nodes, while they have 1,600 values in there, are tiny enough to fit in any RAM situations, like even efficient on a phone. And that kind of scenario. What that means, though, is that your operating system has a file system cache that caches all the upper levels of the B tree. So whenever we have to jump into the B tree to read or to write, we can jump through the different nodes in memory, and then maybe only for the last jump we have to actually make a seek on disk to get the data out. So this is very efficient again. Pretty cool as well. So, and that's also the reason why CouchDB has no caching layer built in on the file system layer, because the file system cache is always smarter. If you've read the thing from the guy who did Varnish on why what's the other one, Squid sucks, that we can't be smarter than the operating system in this case, at least at this layer. Oh, this is my favorite one. Who here's into backups? Everybody. All the hands up. Everybody, cool. So to back up a CouchDB, you need to install this very complicated tool that we've written for. No. To back up a CouchDB, you have the .couch file, which is the core data storage, and you CP it to your backup location, and that's it. You don't have to stop your database. You just copy the raw file to the backup. And the operating system will just walk through the file and copy it to the new destination when it's done. It's over there. So that is pretty neat. And I'll explain how that works with a second bit. Data operation is very safe in CouchDB. And I already explained about 300 times that we're in a tile append storage, always goes to the end of the file. You remember when we wrote the 2 documents and wrote the footer and everything? If we close the database and open it again for reading later, or if later, we would open the database and read from the back instead from the front. And we would find the footer, and the footer has valid checksums, so we believe it's true, and we can walk the pointers to find our data. But now consider we are in the midst of a writing operation. So we wrote the document, we updated one of the indexes, but not the other one, and we didn't write the footer. And then hardware failure, power failure, software failure, couch failure, don't care, something crashes, we lose, that operation just fails, and we have half-written data to the database. So 1, we never acknowledge to the client that that data was safe on disk, so we're good. And second, when we restart CouchDB, it will open the database file the next time and read from the back. And we'll read from the back and look for a footer. And we know the footer has checksums, so we know what it looks like. And we can guarantee it's consistent. And when it finds like a half-written index and then a bit of document data and then a footer, it'll just take the footer that's valid and discard the rest of it. It will not, the half-written data, it cannot know how correct that is, so it will discard it or just not consider it. And then we will start writing to the database from the last committed footer going forward. This means CouchDB has no equivalent to a database checksum file, because the database on write is guaranteed to be correct as long as the file system or Cosmic Race don't flip the bits on the file system. And then if you use something like ZFS, then you even have security against that. And CouchDB does checksumming on read, so at least you know when something's broken on reading. That happened outside of the control of CouchDB. Yeah, no fix-up phase. So if something crashes, CouchDB just restarts instantly. And that's one of the reasons why CouchDB doesn't have a shutdown procedure. There's no, OK, now shut down the server. What you do is just kill the PID. Like Unix has plenty of ways to destroy a process. And CouchDB's like, yeah, just expect that to happen at any time, and I still guarantee safety. So stop CouchDB, kill the PID. You're good. Maybe don't kill -9, but kill the PID. Kill -9 is also safe, but that has other consequences. So just kill the PID, and you're good. So it's very safe. So there's, of course, one big trade-off, and a bunch of you are sitting like in the tree. When is he going to say about this? We can't have a file that grows forever. My disk will run out of space. Oh, my God. And I keep going on and on the positives. The one big trade-off for this is that we need to run a process that we call compaction. Other databases call this vacuum. It's the same same theoretical thing as garbage collection. We'll have data that is no longer relevant in the database file, but since we never touched the database file, we can't like selectively remove it. So what we do currently, is we will walk the by sequence index and just copy out all the latest data into a new database file. And when that's done, we'll swap out the files, so the database starts using the new database file, and we'll throw away the old one. That's like the stupidest way of doing compaction, but it works really nice. We're currently in the process of rewriting that. The copying phase is a lot smarter, faster, less straining on I/O to make that less of a problem, and we'll see how far that goes. And there's other things that we're implementing that makes compaction a little bit more localized as well, so you have not as much compaction going on. But until we know how that actually plays out for people, we have a mechanism inside CouchDB that lets you schedule compaction that fits your use case mostly. I think we're tracking, what's it called? Fragmentation, so the ratio between actual data and stuff that CouchDB has, and you can say, hey, run replication whenever I have more than 70% fragmentation on that database. But don't do it between 8 and 5, because that's our peak hours. So CouchDB will wait until whatever your main users are gone, and you can do the compaction afterwards. That will work. You do not have to stop the database for this, so this is something that, like the backup, just runs while the database is running, but of course it uses I/O, so that's the one big trade-off that we're currently working on improving on. But I think the number of positive features on the site make it well worth it. So let's look at a bunch of core features. Replication, indexing, the changes feed, and compaction. And compaction isn't technically a feature, but it shows how we're using the by-sequence index. And just to hammer this home, all the core features are powered by the by-sequence index. That's the actual cool thing in CouchDB. And the next slide I'm really skipping because that accidentally got in there. So let's look at replication. We have a database down here. We write a bunch of changes in, write a bunch of documents in here, and we will refer to them by their update sequence. So it goes from 1 to 4. And then we create another database over here, and we'll replicate. And we'll replicate, and we'll tell database B, replicate from database A. And then database B will check its own records. Hey, have I ever talked to database A? Like, oh, no. And it asks database A, hey, have we ever talked? And he's actually, no. And then database B says, OK, give me everything, since 0. So database A will send over 1, 2, 3, 4, 5 over to database B afterwards, and then replication is over. Afterwards, we write a few more changes to database A, 5, 6, 7, and 8 over here, and then we tell database A, hey, replicate from database A. Database B will have remembered, last time we talked, I was at 4. Do you have anything more? Give me everything since 4. And then database A sends back 5, 6, 7, and 8. So we have an incremental update of the replication. That's the fundamental thing that happens over the network. There's a little bit more detail to that, which I will get to after this bit. But let's look at indexing next. We have a database A, familiar scenario. We'll write a bunch of changes. And you have an index over here. So maybe CouchDB has a mechanism called views, which allows you to do one-dimensional secondary indexes derived from the original data. There's a thing called GeoCouch, which does spatial or 2D indexing, works the same way. There's a thing called CouchDB Lucene that integrates with that, same story. And then there's a Solar connector that also works the same way. So this just works really nicely. When the index A notices, hey, I need to be updated, and I'm derived from database A, it asks database A, hey, last time we talked, we never talked, just give me everything. So database A will just send out 1, 2, 3 over to the index. And then we do some more changes on database A. You get the idea, right? And then index A needs to be updated again, and it asks database A, hey, what happened after 4? And then in database A sends all this over. This means a few things. Again, the incremental update. 2, which is like we don't have to look at all the data again. It's very efficient. And 2, what was my point? Lost my point in the middle of the thought. Give me a second. Whenever we make changes to database A, we don't have to also update all the secondary and tertiary indexes in the same operation. So write operations only ever talk to the database. And then whenever we have to update an index, that happens lazily. And if we had a lot of changes, they get all updated in bulk, taking advantage of the bulk operations I showed earlier. So this is way more efficient than doing it one by one when writing. This is also why CouchDB is nice and fast. Third, the changes feed. The changes feed looks like this. We have a database. We make a bunch of changes. And I can make an API call that gives me the list of changes. This is a user-facing feature. There's no more to this slide. So everything I just showed you, you can use in your application for your own needs and purposes. This is really nice for things like activities, again, change logs, any kind of activity streams, that kind of stuff. And then finally, compaction. And here I show a little bit more detail. We have a database. We write document A. We write document B, document C. No surprise here. But next, we add a new revision of document A. And at this point, we no longer point to document A on index number 1. So at this point, the by sequence index starts at 2 and then moves forward. So each document is only counted once in the by sequence index. And then we add another document D and another document B, and boom, number 2 gets grayed out as well. So we start at 3 now, and so on. And if we have to do a compaction, we start it in a new file over here, and we just walk the by sequence tree, 3, 4, 5, 6, 7, 8, and voila, we have a new database file that's smaller than the previous one. Compaction is done. If the update of A, for example, was a delete that was marked over here, at the point of compaction, that data is actually removed. So this is how we get around that particular thing. So with this, we'll jump to another data structure that's also a tree, but not the B tree. And it's tiny, and the operational consequences are insignificant for here. But this is the thing that makes the replication magic work. And I initially didn't want to show that, but I thought it was a good thing to do. So I'll try my best and have a nice white slide again. And we'll start with database A. We'll write a document. And this time, we also show the revision ID of that particular document. And revision IDs start with an integer that's incrementing as the revisions go forward, and then a hash of the document. And I abbreviate the hash with A over here. So the revision of document A at this point is 1A. We write a new revision of the same document. We're only looking at a single document here. The new revision is called 2B. But we also carry around the information that the previous revision was 1A. So we know 2B came after 1A. We don't carry around the actual data that was in there, but the information that that revision came before. And we write a new revision called 3C. And again, it succeeds 2B and 1A. We keep that around. Now, we replicate this to database B. We only ever replicate the latest version of a document, version or revision, potatoes. So this is just a pristine copy of the same document with the same history, now on database B. And we make a change on database B, because in CouchDB you can write to any database as if it were a master database. And we'll write version 4D, and it has the same history as the previous version, of course. And then we replicate that back to database A. And at that point, CouchDB sees that the history of the revision 4D matches the history of the previous version here, so we can, in Git terms, fast forward this document to the next one, and all is well. So, and this is the fundamental procedure. I just showed only 2 nodes here, but this can be any number of databases, and they all work in the same way. And the history tracking all makes it work nicely. So this is a list. I said revision tree. Show me the tree. The tree is interesting when we have to deal with conflicts. And a conflict is a state of data that is natural in a distributed system. If you write to multiple locations, data can be in conflict. End of story. There isn't anything bad to it. You just need to know how to deal with it. And I'll show you how CouchDB deals with it. Blank slate again. Database over here. We make our 3 edits to document A. Same situation. We replicate it over to database B. This is same as before. So again, 3C, 2B, 1A, all over here. We'll make a change. Still the same. But then database A also, we make also a change, and we call it 4K instead of 4D. So this is the same it's both the 4th revision on each node, on either node, but it's a different one. Make a different change on both sides. So no, logically, this document is in conflict, but the nodes don't know anything about this until we replicate back from B to A or the other way around, but I show back from B to A. The next step here is CouchDB detects that these 2 documents are now in conflict and keeps around this thing. The history tree for 4K and so on, and the history tree for 4D and so on. So this is where it's actually a tree now. We have two heads in that tree, or 2 branches in that tree. And CouchDB is smart enough to see that the history is mostly the same. So actually, it stores this. So it knows only the revisions 4K and 4D are in conflict. And now CouchDB tells us this document is in conflict by updating the JSON structure in there. It does a few more magic things, but the next step that we're going to do as users is resolve the conflict, like in version control, when you have the big equal markers that are guaranteed to not compile. That you need to resolve this before checking code back in, or like, your friends and coworkers are going to be mad at you. So there's 3 scenarios how we get out of here. First, we say, yeah, that thing is actually cool. Remove the brackets. So 4K is actually the revision we want. 4D, we say this is a previous version. We'll just keep it in the history, but we don't have to have the values anymore. So we'll resolve this to 4K, 4D, 3C, 2B, 1A. Or we say 4D is actually what we want, and it should supersede 4K, 3C, and so on. So we can write that, so one of those. Or we take both 4K and 4D, and by some application-specific logic, merge the 2 files. And as you know from merging source code, this isn't, at a certain point, no longer possible to do this automatically. You can be very clever, 3-way merges and everything. But at a certain point, a human has to decide which data is correct. So in this case, we can do a merge, or even if the computer decides what to merge, actually that works too. We can create a new revision, 5L, which is marked as superseding for both 4D and 4K. And moving on from there. If we replicate the last one, one of the last ones back to B, CouchDB will see, oh, this is either of these is a logical child or successor to the last version I have, so I can fast forward as well. So this conflict is now resolved and can be replicated into the whole system moving forward. This, again, uses 2 nodes, but you can have any number of nodes, and we can have any number of conflicts within per document. And that tree, that slight gray thing here, or the one on top of it, will just have more entries in the brackets or more brackets, depending how deep the conflicts go. This is modeled as a tree, so when you start resolving it, you could just start on one end, and basically do an infix, prefix, I think it's prefix traversal of the conflict tree or the revision tree, and then you can resolve all the conflicts eventually. So this is a deterministic solution possible. That's what makes the replication magic work. I have like 6 more minutes, I think. Briefly, CouchDB is written in Erlang. Who here writes Erlang? All right, a few. That's cool, but that's part of the problem. We picked Erlang early on because CouchDB had a very small development team. The number of developers of most of CouchDB is 1. One guy wrote most of CouchDB back in the day. And he chose Erlang because it allowed him, as a single person, to write a fully capable database system at that point at around 20,000 lines of code. So obviously, he's very smart. 2, Erlang is a functional programming language. That means code tends to be a little bit terser while still being very expressive. It's very efficient to use in small teams. There's still around 10 to 20 core developers of CouchDB, which is tiny for a database. Current code count is about 50,000 lines. So it's still very tiny for a fully capable database that has this and many more features. Erlang has a few more other things that are pretty cool that have made their ways into other programming languages. It implements an actor model before there was an actor model. So there's little tiny processes that run independently. That has a few consequences again. One, if there's an error in one of the processes, none of the other processes are affected. There's a thing called a supervision tree, which connects all the processes in a way that you define, and one supervises the other. So if you tell someone to do a job, that will actually say, OK, I'll do the job, and then we'll actually tell somebody else do the job. And when that fails, and that gets reported, and if it's an error that, oh, we'll just try again and ask another person to do the job, then and that succeeds, we'll refer back to the caller. But if the error over here is one that we can't recover from at this point, we'll just fail as well and report the error back. This is kind of very efficient management structure for building fault-tolerant systems. It's really cool. And then, because everything runs in independent little processes, the Erlang virtual machine can spread that whole computation load over as many nodes or CPUs and cores as your system has. This is really neat as well. So I think the current limit is a couple of hundred something cores for the VM. Where if you add a core, it will just get so many % faster linearly. And then it's implementation details in the VM that make that go away. But if you have machines with more than 200 cores, then it's OK if that's a limit for now. But the VM team keeps working on this. The nice thing is the language and the implementation doesn't have to change. So your code just is the same whether it runs on a single core, 2 cores, 10 cores, 15 cores, 100 cores. It just gets faster magically. Actually, magically. And it has a portable runtime, so it runs on all the Unixes, the Windowses, the Macs. It even runs on phones if you want to, embedded systems like the Raspberry Pi, which is pretty cool. The downsides of Erlang, sadly, it's kind of hard to recruit for. You just saw the few hands here. This is a rather specialized audience, so it's kind of hard to get people for it. It's a bit, if you're new to it, it's kind of hard. If you've been infected with Java bullshit first, it's kind of hard to get your head out of this. Sorry, Java people. There's other bullshit as well that gets you hard, but that's kind of like the big one. It's a bit of an operational black box, and this is actually like a what do you call it? It's actually not bad. There's the famous story you may have heard from the British Telecom that made a study on how good their Erlang routers were working, and they came up with this magic number of 9 nines of availability, meaning the servers were only down less than a second per year, which means they were never down. And that led to things like the operational engineers never having to fix anything, which led to never learning how to fix anything. So you're in a bit of a chicken and egg situation here. You want to be prepared for when something goes wrong, but you never get to train because nothing goes ever wrong. So they have to inject random failures into the system to actually learn troubleshooting, which is an interesting management problem. And yeah, that's about it. There's a few things we can do better in CouchDB, but I'll spare you the details and leave you for questions if you want. So far, thank you very much. This is it.